Okay, I'm back. And we're talking about temperature now. Temperature, the receptors for temperature are called thermoreceptors. Essentially, they are also free nerve endings, meaning they're not really covered in anything, scattered immediately beneath the surface of the skin. They're also in skeletal muscles, your liver, and your hypothalamus, believe it or not. So they are present in some visceral organs, but also present mostly in the skin. There are two actual separate thermoreceptors. There are specific thermoreceptors designated for cold temperatures, and there are thermoreceptors designated specifically for warm. Cold tend to be more numerous than warm, but they're structurally the same, just specifically meant to receive cold signals. They are very active. If you've ever noticed, as soon as you walk in a room where the air conditioning's on, you instantly know that the air conditioning's on and there's a temperature change. There's no time frame to receive the stimuli. I mean, it's instantaneous. It has the same pathway as pain, and it's uncommon for you to actually have conscious awareness of temperature. And I can show you this by, if you go back to that air conditioning example again, if you go from outside in the summer and it's 100 degrees and you walk inside where the air conditioning's on, you actually can notice instantly, it's brought to your conscious awareness that there's a change in temperature, but after time you could become completely unaware. So it's very active, but at the same time, it's not necessary that it's always brought to your conscious awareness. If you notice here, pain are still a little bit more superficial, but you have thermoreceptors specifically designed for heat. You have thermoreceptors specifically designed for cold temperatures. Touch pressure and position. Mechanoreceptors are those receptors sensitive to stimuli that distort their cell membrane. So these aren't necessarily free nerve endings. What they are is the nerve endings have some kind of cell membrane on them that when it is distorted, it picks up the stimuli and then creates an action potential. There's three classes of mechanoreceptors. The first kind are called tactile receptors. They're more specific for touch, pressure, and vibration. There's a couple of different kinds. You have fine tactile receptors, which these provide info on the exact location, shape, size, texture, and movement of objects or stimuli. And then you have crude, which have poor localization, very little stimulus information. And what I did in our lab is I tried to bring this to light with you with the marker example, where you had various regions on your arm where you had to close your eyes, your partner put a dot, and then you had to try to match that dot in some way, shape, or form, which became kind of very difficult to do because of the fact that throughout your skin are very different times of tactile receptors. There are free nerve endings. There are also root hair plexus. You have tactile receptors on the ends of the roots of your hair, and their sole purpose is mostly so they can actually detect when hair is moved. And you know those are very sensitive stimuli because you can actually feel just the slightest breeze or the slightest blow of air from somebody's mouth on your skin when the hair is moved. There are tactile discs, which are for fine touch or pressure, and then there's tactile corpuscles, which are for fine touch or pressure also. Tactile corpuscles are more abundant in places like your eyelids, lips, fingers, nipples, and external genitalia, whereas laminated corpuscles are for deep pressure and vibrations. Those are more abundant in your fingers, breast, external genitalia, joint capsules of your body, pancreas, and urinary bladder. And if you think about it, the urinary bladder pressure is kind of an important thing to realize. You also have Ruffini corpuscles for pressure and skin distortion, but they're in the deepest layers of your skin. So if you're looking at this diagram here and you're wanting to label kind of what each thing is, you should know that A, which is located right here, are the free nerve endings. B is going to be the root hair plexus, which if you notice here's the hair, it's in the hair root and it's wrapped around the hair, so when the hair is moved or in any kind of way changes direction, an action potential is sent down through the nerve. You have C, which are the tactile discs, which are up here. You have D, which is the tactile corpuscles. If you notice, they have a large membrane around them that require distortion of that membrane to pick up any kind of stimuli. You have laminated corpuscles, which are E, a little bit deeper, And then you have Ruffini corpuscles, which are actually even deeper than those. Another kind of mechanoreceptors is going to be baroreceptors. These monitor changes in pressure. Do not confuse these with those that are associated with tactile discs. Those require distortion. These types, or baroreceptors, are typically paired with some kind of elastic tissue in the walls of a blood vessel, digestive or urinary tract, and lungs. These monitor changes in pressure of a lot of visceral organs instead of the superficial structures outside of the skin. So a baroreceptor would not be used to monitor the pressure placed on your hand from somebody else's hand, or by squeezing with the hand you monitor pressure. Baroreceptors typically would not be used for that. Again, so you have tubes, you have blood vessels. This is like where your blood pressure is monitored. Your blood pressure is actually monitored by your kidneys, so there are several baroreceptors within your kidney, your ureters, your urethras, your urinary bladder, all of those structures that can fill, expand, and contract and have to have a monitor and pressure. Also your lungs. If you take a really, really deep breath, you will notice that you can detect the pressure that is inside your lungs very easily. There's also pressure within the aorta, which is a big factor because the aorta receives a lot of force generated by the left ventricle to push blood out to the body, so pressure on that one has to be monitored rather well, and baroreceptors do that. Oops. Then we have proprioceptors. Proprioceptors, I think, are the most interesting ones. These we kind of touched on briefly when we talked about cerebellar ataxia and the fact that your cerebellum maintains the position of your body and posture throughout the day at a subconscious level, or without you realizing it. Proprioceptors monitor the position of your joints, tension of ligaments and tendons, and the state of muscular contraction. And what I think is interesting about this is they continually send information to the central nervous system, particularly the cerebellum, and combined with some other structures, and it's mostly processed at the subconscious level. Something that's really cool is they typically don't adapt. You don't want this to happen because then you could lose posture. And two videos that I wanted to show you that kind of test proprioceptors and their ability to relay information effectively to the cerebellum, which if they don't, it can indicate cerebellar ataxia, is called the Romberg test. So I'll watch this video here on the left really quick, and it kind of goes over a Romberg test where the person has normal function, and then we'll watch one where the person has abnormal function in a Romberg test. As you can see,
let's have you go ahead and climb down. Very good. And I'm going to have you just put your feet together and close your eyes and hold still. And I'm going to now tap you.
You gotta love the network. Well, let's say that this actually worked and wasn't buffering. What would happen is you would see that as he taps her on each side of her body with her eyes closed, you will notice that she maintains balance because the proprioceptors within her joints, muscles, and whatnot will actually send signals to the cerebellum or to the central nervous system telling her to adjust accordingly to maintain balance while her eyes are closed. Now let's see if this video will work, which it probably won't because I need it to. This is a Romberg test with a subject who definitely has cerebellar ataxia, and you will notice that when they start the test with this person with their eyes closed, not even tapping them, their body lacks the ability to maintain posture and balance because the proprioceptors lack the ability to accurately communicate with the central nervous system. Okay. Then you have chemoreceptors. Chemoreceptors are responsible for detecting chemicals, particularly dissolved materials. The big ones here are going to be things like carbon dioxide, oxygen levels, pH levels, things like that, and it's usually involved with like your blood. But they usually adapt rather quickly. They're most importantly, like I said, measure carbon dioxide, oxygen, and pH levels. Remember, pH is the level of acidity or how basic your the tissue or the fluid within your body is, and you need to maintain a very precise pH level in your body in order to maintain homeostasis, and it is slightly basic. It's a little bit above 7, but mostly kind of stays around neutral. There are significant chemoreceptors located in the medulla oblongata, carotid bodies, where these are the arteries in the neck right here. You can feel a giant pulse in the aortic bodies of the heart, because they need to monitor the levels of carbon dioxide and oxygen and things like that in order to accurately adjust for homeostasis, causing the heart to beat more, increasing respiratory rate, things like that are monitored by chemoreceptors. And that is the end of this presentation. If you have any questions, let me know. Other than that, I hope this helps.